Okay, let us start with the uh, fourth chapter that is in filtering in a frequency domain. And okay, previously in a second chapter, we have in a third chapter, yes, in a third chapter, we have done filtering in a spatial domain, which represents the image itself. And in this chapter, we will do the filtering in a frequency domain. And it includes the Fourier series, Fourier transformation, discrete Fourier transformation, and the fast Fourier transformations, and the various filtering procedures involved in the frequency domain of a digital image processing. And in this chapter, we are going to learn about the. Okay, just hold for a second. Okay. Yes. Okay. Let us begin with the Fourier series. Introduction to the Fourier series. And a Fourier contribution in the Fourier contribution in the field of a digital image processing that involves any periodic function that can be expressed as a sum of sine and cosine of the different frequency and each multiplied by a different coefficient. It is called as a Fourier series, and the functions which are not periodic and that are expressed in the form of integral of sine and or cosine multiplied by a weighted function. And hopefully you already have done this in signal line systems, that is the Fourier series and the Fourier transformation. And there is a one more important property. Both representation share the important. Uh, okay. Both the representations share the important characteristics that a function expressed either in a Fourier series or a Fourier transform can be reconstructed or recovered completely via the with the help of a inverse process without any loss of information. And the discrete Fourier transformation is a discrete version of the Fourier transform that transforms a signal or a discrete sequence from the time domain representation to its representation in a frequency domain. And whereas the fast Fourier transformation, there is any efficient algorithm for calculating the DFT, discrete Fourier transformation. Now, the fast Fourier transformations come into existence in early 1960s, and they have made a significant contribution in the field of signal and image processing. And what is the fast Fourier transform? Fast Fourier transform is an algorithm that computes the discrete Fourier transformation (DFT) of a sequence and its inverse form, that is the inverse DFT. And the Fourier analysis converts the signals from its original domain, that is whatever we have covered in a previous chapter, that is a spatial domain in case of a digital image processing, and from its original domain to a representation in the form of the frequency domain and vice versa. So why there is a requirement of a there may be a question why there is a requirement of uh, covering this frequency domain in a digital image processing if we can do each and everything with the help of a spatial domain processing. Now the question of this answer is very simple because there are many operations which can be performed in a frequency domain but not in a spatial domain. So in that scenarios, we have to convert uh, a spatial domain image or a original image into the frequency domain, and we have to apply some mathematical equations and then convert it back into the spatial domain so that we can visualize. So there are some specific operations which are available in the frequency domain but not available in the spatial domain. So that's why we are using the frequency domain in a digital image processing. And but it is noted that we have to first convert the spatial domain into the frequency domain to perform the mathematical operations and then reconvert back into its original form so that we can visualize the results. So this is a just a basic towards, and hopefully you already are well aware about that. What is a Fourier series? What is a Fourier transformation? DFT and there is IDFT and FFT. So these are the all important terms which are going to be used in a digital image processing. And this is the first one. Here you can just check it out. There is a first figure which represents the function box, and there is a Fourier transformation of the this function box. And the further there is a third one is representing the there is spectrum. For you can you can see that there is a spectrum of this function. And what is a spectrum? The Fourier transformation contains many complex terms, which represents the magnitude of transform, and is called as a Fourier spectrum, and it is represented here. And here you can just easily compare that the signals. What is the difference between Fourier transform and the Fourier spectrum? It's there is no any big difference, but the magnitude on a positive side. Okay, the next part of the field in a frequency domain, that is how to convert a signal into the uh, in the form of samples, and we have already covered this topic in some earlier first or second PPTs, but that is a very clear to you. And this one is an analog signal, and this is multiplied signal, which is a impulse train of impulses, and this is a product form. That is a product of a figure A and figure B. Or figure A is this one is a figure A, and figure A is an analog signal, and the figure B is an impulse signal. When they both are multiplied with each other, then it will look like that. And the last one is nothing but just a there is a sampled form of this analog signal. And hopefully you all have got this point. And the Fourier representation of the sample function can be donated as a can be donated in the form of this representation. But at the end of PPT, you will get some formulas where you can estimate the different Fourier transformation functions as well as the Fourier series functions. Now let us start with the sampling theorem, and hopefully you all are aware of that. What is the sampling theorem? And in a simple terms, we can say it as a continuous signal can be represented in its sample form and can be converted back to its original form. The only condition is that when the sampling frequency there is fs, there is fs is greater than or equal to the there is twice of the highest frequency of the message signal. This one is a message signal. So this is a standard formula that is mentioned here, that is equal to or greater than. But please note that now in a sampling we have already know about there are three types of the outputs we can expect from the sampling. That is oversampling, that is perfect sampling, and the undersampling. And what is the difference between them? That is simple. The difference is all about the equation. If the sampling frequency is less than the twice of the modulating or message signal message frequency, then that is a undersampling. And if it is equal to the twice of modulating same frequency, then we can say it as a perfect sampling. And yes, please note that. And we also know this term as a critical sampling. And the third one category, which we can expect from the sampling theorem, that is oversampling, in which the sampling frequency is greater than but not equal to or less than, that is twice of a message signal. Then and the signal is look like that. There is a gap in between the samples, and there is no any gap. There is a critically, and this one is a under, when the signals are overlapping with each other. And this is a demonstration of a Fourier transformation of a band limited function, and in which the transforms of the corresponding sampled function under the condition of oversampling, there is oversampling, and there is a critical sampling, and this one is a third one is a undersampling. So this is the representation. And yes, the Fourier transformation is a sampled form. Definitely, this is uh, a little bit, we can say it as a, there is a required format for a sample form, and we can pass the signals with the help of there is a low pass filter, ideal low pass filter. And as you already know about that, in analog and digital communication, or in if you have done the digital communication, then we can say it as a, there is a in order to convert the analog signal into a digitized format, there is a requirement of a low pass filter. And what is the function of low pass filter? That passes the, that is a required low band frequencies, and uh, that is a too specific. Here you can just check it out. This one is a required band, uh, and in this we are using the, there is a low pass filter, there is a transfer function, and in which passes only the required frequency and discarded the, there is, if there is any other uh, information available on the sideband or undesirable position. So yes, there is a one important, more important aspect in digital signal processing or in a digital image processing, that is a ELAS. And what is a ELASing? That is a false identity. And in the field of signal processing, the ELASing referred to as a sampling phenomena that causes the different signals to become the indistinguishable from one another after the sampling. So what is that? And normally we can also say it as a, there is a, when this condition will arise, this when the sampling frequency is less than, or if it is not equal to or greater than uh, uh, that is a twice of the message signal or message frequency, then there is a problem of a aliasing. Here the cross one that is representing the aliasing case. And aliasing, in a aliasing, here you can just see it as a, with the help of another example, in which here you can see that there is an input signal, that is an analog signal, and definitely this is a high frequency signal. Yeah, here this is a high frequency signal, and this one is a output sample form. And this one is in a bottom figure. There is a low frequency signal, and this is a correspondingly sample form. And here you can see that the both the sample formats which are given by these two different frequency signals are same. So there is a problem in aliasing. What we can expect. as an error in a signal processing. And we can just go through with this. This is a impulses and this is a sample. And here you can how this sample signal has been formed with the help of the this impulse responses. And here you can just check it out the position of both the signals the when it strikes through the plane of impulses. It is just look like at a same position, but in actual there is a difference between these two signals, but their sampled output is same. So that is a problem in a digital image processing as well as in a digital communication, and which creates the effect, undesirable effects. So this needs to be avoided in the uh, signal processing as well as in the image processing. Now there is a aliasing effect in the images, and what is that? Here you can just see it out. There is a first figure which is composed of there is a 772 pixels into the 548 pixels, and with the negligible aliasing. And here we are not considering that is consider it as a simple digital image. And then we have reduced this image to 33% and then restored back towards this toward its original position. Means there is a figure A is first of all reduced to the that is reduced to the 33% quality. Then it has been recovered back to its original position, or we can just say it as a there is an increase to its original position. That is around we have put it as a 100%, and then here you can just see the output that is in figure B. Means the figure A, first it has been reduced up to the 33% and then again enhanced to the 100%. And how this image look like that? And is as shown in figure B. And here you can just see the aliasing effect. And what are those aliasing effects? And here you can just check it out through this texture. So if we have compressed an image and then recovered back to its original position, then there is a different kind of information. So there is a aliasing effect in the images, and there is another figure that is representing in a figure C. There is a blurring. There is a blurring. They have applied the averaging operation to blur the image on a figure A, and then uh, got the figure C. And when they have got the figure C, and please note that they have actually smoothed the image. That is in this you can when you are checking this point, it basically smooth the image, but yes, definitely there is no any misinformation in the texture. If you we are comparing these three tiles, that is tile A, tile B, and tile C. And if you are just checking out that the figure B is representing the little bit false information, and this is due to the aliasing effect. And please note that in a figure C, the image has been blurred, but please note that there is no any aliasing effect or a negligible aliasing effects are there. So the in this case, the aliasing is not longer the objectionable. Uh, so that is a critical information that we need to be work upon it. And now there is another important. Uh, okay, there is the next question: how we can remove the aliasing effect? And your answer will be that is with the help of a low pass filter. And what are the why we are using the low pass filters? In a we have already done this in the spatial domain, and we are using the low pass filter, high pass filter for the image smoothing and the sharpening purposes. And here we are using the low pass frequency domain filter to smooth the image and with the help of a low pass filter. And here we are just a definition given to you, that is smoothing or blurring is achieved by the frequency domain, and that is represented as a low pass filtering. And we have in a digital image processing, we have three low pass filters. That is the idle, Butterworth, and the Gaussian. These three, and these three categories cover the ranges from the very sharp to the very smooth filtering process. That is from idle to Gaussian. And this is a brief equations which are required to perform the low pass filtering operations uh, in a frequency domain of a digital image processing, and where D naught is a cutoff frequency and N is the order of the Butterworth, which actually represents the what there is a number of or there is a quality of blurring is required, and we will do this in little bit details. And the 2D filter, first we will take the example of idle low pass filter, and definitely it passes the information. Uh, yeah, well, first of all, they have take the example of this in this case, and in a 2D low pass filter, it passes the information without attenuation within the circle of the radius from the origin, and cuts off all the other frequency outside the circle, and it is called as a idle low pass filter. Means that is given to you that they have just block all the frequency outside of their circle and just pass all the frequency within that circle, and this one is achieved with the help of this equation by applying the cutoff frequency, and there is a positive constant, and the du v is actually obtained by this, but it is a distance between the point uv in the frequency domain and the center of the p and q frequency rectangle. And this is the first we will go through this figure, and there is a perspective plot of there is first one, there is a perspective plot of a low pass filter, and second one is a function displayed on an image, how it look like on an image, and the third one is a radial cross section which passes the uh, low frequency and reject all the frequencies higher than this cutoff frequency. So the main role of this D naught. Oh, sorry. Uh, one second. Uh, so the main role. Okay, where we are now. Okay, the main role in filters, that is a D naught, which decides the or we can say it as a there is a cutoff frequency, where we can say it as a from beyond at what frequencies the frequency will be allowed and rejected. And there is another case, there is a part of a low pass filter, there is a Gaussian filter, and which is achieved by this equation, and this u is just a difference as in existence model, and just we go through these output figures and how the outputs look like. And that is yes, please note that there are different values they have been used, and we can just go through all the values, and this is a function displayed on an image. That is a uh, kind of a smoothing image. And the third one is a Butterworth filter, definitely, in which the order is also an important factor, and with the frequency, with the cutoff frequency. And here you can just check it out, these graphs, and these graphs are important to you when you are comparing these three filters, low pass filters, that are idle, Gaussian, and Butterworth. Please just go through these output plots and how these outputs are plots are changing with respect to the different values of the this is with respect to the order, and this is with respect to the cutoff frequency. So there is some other examples where we can just go through it. And yeah, this is an example of a low pass filter. There is a Gaussian low pass filter. There is the original image, and another one is a there is in which we have used the cutoff frequency 150, and there is a, smooth image there is a figure B smooth as compared to figure A, and the figure C is smooth as compared to figure B. But here you can just check it out, and please note that in third we have used the filtering operation, that is a 130, and you can just reduce the value, or you reduce the cutoff frequency to smooth the image. And please note that while we are doing the smoothing, there is a reduction in the fine skin lines in the there as shown in the magnified section. There is a reduction in the see 20. So that has been decreased further. Just hold for a second. Okay, now there is these are the uh, low pass filter. There is examples of a low pass filter, and please note that now we are doing the image sharpening with the help of a high pass filter. And again, these are again divided into the three categories. That is the idle, Gaussian, and the Butterworth. And in the previous section, we have done smoothing by attenuating the high frequency component of its Fourier transformation. And now in this, we are doing the image sharpening, and in by using the high, high pass filter, and which attenuates the low frequency components without disturbing the high frequency in the Fourier series. And once you just go through the comparison between these two, that is these two models, you can just analyze what is the difference in between them. Uh, Here, that is when do you, one second. Yeah, here you can just, when you are checking, you can just go through these two values have been changed with respect to the passing operations. And here we have just reversed these two values, and we can check out the comparison between all these three values. And there is a first one is representing the idle. There is an idle high pass filters, and this one is a Gaussian high pass filter, and the last one is a Butterworth high pass filter. And we have used these three operations to obtain that particular operation. And yes, there are some details which are important to you, and you may have already done this in a signal and system chapter. There is some symmetric properties of the two-dimensional DFT and its inverse in a spatial domain as well as in a frequency domain. And here you can just do the comparison between these two values, these two domains, that is a frequency and spatial. And there is examples of the some of the properties that is of spatial and the frequency domain. And the another one is different parameters involved in the DFT. There is inverse DFT, there is spectrum, phase angle, polar representation, power spectrum, average value. You can just go through these important terms. And yeah, these all are related to your base. And please note that in this digital image processing, we are highly concerned with these three filters. that is image smoothing with the help of a idle low pass filter, Gaussian low pass filter, and the Butterworth low pass filter. And another one is a image sharpening with the help of a high pass filter in with the help of a idle, Gaussian, and the Butterworth high pass filter. So these are the important topics, and for your reference, I have just added all these equations at the end of the PPT. You can go through it if you are not aware of the different functions that we have already done in a single line system or in a digital image processing. And if it is clear to you, then there is no big problem in going through or understanding of this chapter. And hopefully, you are getting the uh, understanding of the frequency domain in digital image processing. And previously, we have done filtering in a spatial domain analysis. And in the next chapter, we are going to do the image recover. That is a third or fourth step. Yeah, that is a third step in digital image processing, and your fifth chapter. Now, if you have any question, then you can please feel free to ask, and um, you can also write it on a chat box, or you can ask me directly. And uh, if you don't have any question, then you can please mark your attendance. The all links are active now, and if there is any query regarding the syllabus topic or this topic or previous topics, then you can please feel free to ask. Hopefully, the links are already you already have the attendance link. And if you don't have, then just I will give it to you. Just hold for a second. Yes, everyone, please mark your attendance and confirm me. And if there is any question, then you can please feel free to ask. And your expected uh, date of ST1 will be on next week. There is only expected, not confirmed yet, but you can just be prepared about that. And up to 18th lectures of with respect to the course handout, those topics will come under the ST1, and you just have to go through the course handouts. And I will also uh, I will also review all the lectures in discussion session in this week. And if you have any query, then you can please write it down, and you can ask me on that particular discussion session, or you can also write it on a Google Classroom. And if you have marked your attendance, then you can leave the session